Sorry for the technical difficulties. Let's continue where we left off. So these are the 10 axioms for a vector space. These are the 10 axioms that need to hold. And this was the end of the definition from the last video. So let's keep going. And so let's keep going. Okay. Okay, so continuing, let's look at an example of a vector space, and that's the zero vector space. Okay, so this is our first example of a vector space. Okay, the zero vector space. And so the zero vector space is just the set containing only the vector or number 0. Okay, addition is defined the usual way. So addition is defined as being, if you take the number 0 and add 0 to it, you get 0. And scalar multiplication is k times 0 is equal to 0. Okay, all 10 axioms hold for this vector space. Okay, so it has closure for addition. So if you add two zeros, you get 0. That means that you take any two objects in V, which is only 0, and you add them, you get another object in V, 0 itself. Commutativity holds. So if you switch the order, the only thing you can add is 0. And so U plus V equals V plus U holds because 0 plus 0, you switch them, it's the exact same thing, 0 plus 0. So the second condition holds. The third condition is associativity. And again, there's only one element, and so this is really, that definitely holds, right? And so associativity holds. The fourth one is the identity operation. That's just saying there's some vector called 0 that you can add anything else in the vector space and get 0. So the identity one holds. The fifth one is that any object in the set which is only 0 has an inverse element you can add to it to get 0. So the identity also works. The inverse one also works. 6 is that has closure under scalar multiplication. 7 is that k times the sum of two different vectors is equal to this. That also holds. And then 8, if you have two scalars and you add them and you multiply it by a vector, which is the only choice you have for an object in V is 0, and that's the same as k times 0 plus m times 0. And so that also holds. And then 9, the ninth one, that k times m times 0 is equal to km times 0. That also holds. They're both 0. And 10, 1 times 0 is 0, and that also holds. So if you look at all 10 axioms from the definition of vector space, all 10 of them hold for the 0 vector space. Okay? So if you look back in the video at the 10 axioms, and you the only vectors you can choose, the only objects in V you can choose are the 0 vector, and you can choose any scalars k and m. All 10 axioms hold. And so the 0 vector space is a vector space. And that vector space consists of the set V, which is just containing only 0, the operation of addition, and the operation of scalar multiplication. That's scalar multiplication. So scalar multiplication. That's what that operation is, okay? And so a vector space is the team of those three things. It's not just the set, and it's not just the two operations. It's the set and those two operations combined. Those three things together make up a vector space. And so this vector space is the set containing only the number 0, this operation of addition, and this operation of scalar multiplication. Those three things make up the 0 vector space. And it is true because, again, all 10 axioms hold. Okay. Okay, the book also has all 10 axioms written down, and so you can refer to the book on page 184, and that will show you also has all the axioms written down. So in example 7, in the section 4.1, it's an example of a set that is not a vector space. Okay, so when it says a set here, right? Mathematicians are intentionally lazy when it comes to talking about vector space. So intentionally, mathematicians would rather take the lazy approach to talking about vector space than say everything there is to say in order to really say they're talking about vector space. Meaning, if you have a vector space, a set V, an operation of addition, and an operation of scale and multiplication, a vector space does consist of those three things. That makes a vector space. But a mathematician would rather be lazy and just say V is a vector space and not mention the other things involved, because it would take longer to always say all this information every time I was referring to the exact same thing. So mathematicians, for short, will refer to a vector space as the set. But what they really mean is all three things, okay? So you'll always see, almost 99% of the time when someone talks about a vector space, they're going to talk about the set. But what they really mean is this team of three things every time they refer to a vector space. They're being lazy intentionally to save time so that they can get more done faster. Okay? So let's keep going. So let V equal R squared, and define addition and scale and multiplication. Operations as follows. Okay, so if U equals U1 comma U2, and V, then define U plus V is equal to U1 plus V1 comma U2. Okay, so we're going to define addition on two vectors in this way. So if we have this vector U and this vector V, we're going to define addition to be adding their first components and then adding their second components, like this, okay? And then, and if K is any real number, then define this to be scalar multiplication. Okay, so we're going to define this to be scalar multiplication. So I'm going to take a scalar K and multiply it by U. And we're going to say the first component is going to be multiplying the first component of U by K, and the second component is going to be 0. Okay? And so this is how we're going to define addition, and this is how we're going to define scalar multiplication. Okay? And the set is R2, the set of all two tuples. Okay? So our vector space, or what we're considering to be a vector space, is the set R2, this operation of addition, and this operation of scalar multiplication. Okay? And so we're going to show here that this is not a vector space. Okay? And so the first 9 axioms hold. But the 10th one doesn't. Okay? And so what I'm going to show is how the 10th one doesn't hold. Okay? And so when I show you that the 10th axiom for a vector space fails, then not all 10 axioms hold. And once that happens, you do not have a vector space. In order to have a vector space, all 10 axioms have to hold. Okay? And so by showing that just the 10th one fails, means I've shown that not all 10 are true. Okay? And so the next word I'm going to show you why the 10th one fails, and that will mean that we do not have a vector space. Okay. Okay, so if U is equal to U1 comma U2, such that U2 does not equal 0, then 1U is equal to 1U1 comma 0. Okay, our definition, our scalar multiplication is defined as k times u is equal to k u1 comma 0. That's our operation of scalar multiplication. We multiply the first component of u by k, and the second component is 0. And so 1u is 1 times the first component, comma 0. And I chose u so that its second component was non-zero. And so this resulting vector is not equal to u1 comma u2. Okay? The first components are the same. 1u is u. Regular multiplication of 1u is the same as u. But 0 does not equal u2 because that's how I defined u. Okay? And so this is u. And so what this says is that 1u does not equal u. Okay? Axiom 10 says, what axiom 10 said was that 1u has to equal u. Right? That's axiom 10 for a vector space. And what I showed here is that 1u does not equal u in this given possible vector space. And so the conclusion then is that our v comma plus comma times is not a vector space. Okay, so the conclusion is that is not a vector space because axiom 10 fails. Okay. Okay. So the next theorem is theorem 4.1.1. Let capital V be a vector space. U a vector in capital V, and K is a scalar. Then, so for A, 0u is equal to 0. B, k times 0 is equal to 0. C, negative 1u is equal to negative u. Okay? So we have these three equations in theorem 4.1.1. Okay, and D, fourth one, D, if ku equals 0, then k equals 0 or u equals 0. Okay, so if k times u equals 0, then k equals 0 or u equals 0. That's D. Alright? So if you multiply any vector by 0, you get 0. If you multiply the 0 vector by any scalar multiple, you get 0. Negative 1u equals negative u. If k equals 0, then k equals 0 or u equals 0. Okay? Okay, so we have those four also. And so that's the end of 4.1. Okay, 4.2 is on subspaces. Okay, so definition 1. So a subset W of vector space V is a subspace of V if W is itself vector space under the addition and scalar multiplication. Okay, so a subset W of vector space V is a subspace of V if W is itself a vector space under the addition and scalar multiplication on V. Okay, so this is the definition of a subspace of a vector space. Okay, so subset W of vector space V is a subspace of V if W is itself a vector space under the addition and scalar multiplication on V. Okay, okay, so okay, so that's the definition of a subspace of a vector space. So theorem 4.2.1. If W is a set of one or more vectors in a vector space V, then W is a subspace of V the following conditions hold. Okay, so if W is a set of one or more vectors in a vector space V, then W is a subspace of V if and only if the following conditions are satisfied. Okay, so if U and V are vectors in W, then U plus V is in W. Okay, so if U and V are vectors in W, then U plus V is in W. B, if K is any scalar and U is a vector, in W, then KU is in W. Okay, so K is any scalar and U is a vector in W, then KU is also in W. Okay, so these are the two conditions that are equivalent to W being a subspace of V. Okay, so W is a subspace of V if and only if we have these two conditions. So if U and V are vectors in W, then U plus V is in W also, okay? And if K is any scalar and U is a vector in W, then KU is in W. So this means it's closure under addition and it's closure under scalar multiplication, okay? So W is a subspace of V if and only if there's closure in addition, under addition and scalar multiplication. Okay, so that's the theorem. So example 1, the 0, okay, so I redid that. Okay, so actually, let's talk about that example. Okay, so if we look at the 0 subspace again, right? Before I proved that all 10 axioms, if you show all 10 axioms, then you know the 0 vector space is a subspace, right? you know the zero vector space is a vector space if all 10 axioms hold, right? But an easier way to show that the zero vector space is a vector space is to show that it's a subspace of a given vector space, okay? So if capital V is any vector space, and if W is equal to the zero set, is obviously a subset of V, because in order for V to be a vector space, it has the axiom of having a zero vector, okay? Right? In the 10 axioms for vector space, one of them is that there's a zero vector. You can add to any vector and get that same vector. So we know the zero vector is in V. So if we define a set W as consisting of only the element 0, then we know that that has to be a subset of V, okay? So W here is obviously a subset of V. Okay, so we have a vector space V and this subset of V, W, okay? Then W is closed under addition and scalar multiplication. Okay? W is then closed under addition and scalar multiplication. If we take the zero vector and add the zero vector to it, we get the zero vector. If we take any scalar and multiply it by 0, we get 0. So what these two equations show us is that I can take any vector in this set, only 0. And if I add 0 plus 0, I get 0, k times 0 is 0. So that's closure under addition and scalar multiplication. And so from the last board, we know that having a subspace is equivalent to having a set that's closed under addition and scalar multiplication, using the same operations of addition and scalar multiplication as the one we had for original vector space, okay? So we had addition and scalar multiplication on this vector space V. And we're going to use those two same operations, but now only using elements in W. And if we have closure under addition and scalar multiplication here, then we know that W is a subspace of V. Okay? 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 And so that implies that W is a subspace of V. Okay, so W is a subspace of V because it's closed under addition and scalar multiplication using the same two operations we were using for V. So W is a subspace of V. A subspace of a vector space is itself a vector space. And so this implies that W equals the zero set is a vector space as a subspace of our given vector space V. Okay? Any vector space V contains a zero element. And so the zero vector space is a subspace of any vector space, okay? And so showing the existence of a vector space, which we technically did because we showed the zero vector space as a vector space. Knowing the existence of a vector space, we can then say that W is a subspace of any vector space, okay? Because in addition to the one vector space we talked about already, any other vector space that would have to exist would have to contain the zero element, okay? So we can talk about an arbitrary vector space V because we already proved the existence of a vector space. And we could then talk about the subspace W of any arbitrarily chosen vector space V. And it being a subspace means it itself is a vector space. So this is a shorter way to prove that the zero vector space is in fact a vector space as a subspace of an arbitrary vector space. Okay? Okay, so you have to look at that. Okay, so we call that W the zero subspace of V. Okay? So that was the zero subspace of V. Okay, let's just keep going. We have table 1 here in this section. And in table 1, we have subspaces of R2. subspaces of R3. Okay, so we're supposed to use R2 and R3. So the origin is a subspace of R2. Lines through the origin are subspaces of R2. And all of R2 is a subspace of R2. Okay. Subspaces of R3 are the 0 set. Lines through the origin. Planes to the origin. And all of R3. Okay, so we have subspaces of R, all the other subspaces of R2 and all the subspaces of R3. Okay, so if you're looking at a geometric object as a subspace of R2, as a subset of R2 or R3, if it's not one of the ones in this list, then it's not a subspace. If it is something on this list, then it is a subspace. So for instance, if you looked at the XY plane, right, R2, and you looked at this line here, right? So we're looking at this example. We'll look at this line here, right? Now, if you look at this table, it tells you what the subspaces of R2 are. It tells you either it's the origin, just the origin by itself, a line through the origin, or all of R2. Well, this is a line not going through the origin. And so it's none of those three things. And so easily, just by referring to this table, you can conclude that that is not a subspace of R2. Okay, so if you believe this table, then you know that that line is not a subspace of R2. And a very easy way to know it's not a subspace of R2 is because it doesn't cross the origin, it does not contain the zero vector. And so one of the axioms was that what has to be, in order to have a vector space, your set V has to contain an element 0. Right? And so we don't have 0 for this line because it doesn't go through the origin. And so right away that axiom fails. And we found, just by knowing this line does not go through the origin, it does not have a 0 vector. And what means it does not satisfy one of the axioms, which means it does not satisfy all 10 of the axioms. Okay? So this line is definitely not a subspace of R2. Okay? So very similarly for R3. If you have R3 here, which has the x-axis, the y-axis, and the z-axis. If you have a plane, let's say we look at this plane, and it does go through the origin, okay, and it continues in all directions, and it doesn't stop. So it goes through the origin, and it's a plane going in all directions, in all 4 directions. This, according to this table, is a subspace of R3. This plane through the origin is a subspace of R3. And so you can show that all 10 axioms hold. Since it goes to the origin, it does have a 0 vector, so that one immediately holds. If you take 2 vectors on this plane and you add them, you're going to get another vector in the plane. So it has closure under addition. If you take a vector in the plane and you multiply it by a constant, you're going to get another vector in that same plane. And so closure under scalar multiplication also holds. And so this plane through the origin has closure under addition and scalar multiplication. And this plane is a subset of all of R3. And I could show you that all of R3 is a vector space. And so knowing that R3 is a vector space and knowing that this plane through the origin has closure under addition and scalar multiplication, I could then conclude from our previous theorem that this plane through the origin is a subspace of all of R3. Okay, so this plane through the origin is a subspace of R3, which means it's a vector space by itself. Okay? A subspace of a vector space is something that is itself a vector space as a subset of your original set using the same operations as your original vector space. So I'm saying a lot, but basically, if you have one of these things, it's a subspace. If you have one of these things, it's a subspace. If you don't have one of those things, it's not a subspace. Okay? 10 axioms have to hold for a vector space. If one of them fails, it's not a vector space. Okay. Okay, so example 5 in in this section. We have subspaces of M sub nn. Okay? M sub nn is the vector space of n by n matrices using usual matrix addition and usual matrix scalar multiplication. Okay? So note, M sub nn, well, so M sub nn is the vector space of n by n matrices with real entries with the usual addition and usual scalar multiplication operations. On matrices, right? The way you would normally add two matrices and the way you would normally multiply a matrix by a scalar, that's the same operations we're using for this vector space M sub nn, right? And so doing this the better way by being a little lazy, I'm being lazy by saying this vector space is a set, but it really means the set along with your operations of addition and scalar multiplication, right? So M sub nn, which is the set, is shorthand for the set and the operation and the two operations. Okay? So that's our vector space. And so thinking of subspaces of M sub nn, you can talk about the set of symmetric matrices. Okay, so the set of symmetric n by n matrices, that is a subspace of M sub nn. Okay? So one subspace of that vector space M sub nn is the set of symmetric n by n matrices. Those are matrices whose transpose equal itself. For instance, an example of a symmetric matrix would be the matrix 1, 0, 0, 1. That's a symmetric matrix because if I take its transpose, it's equal to itself. Okay? Another way to look at it, it's sort of like there's a mirror view of what's in the top right and the bottom left. Okay? Another example of a symmetric matrix would be this one. That's another example of a symmetric matrix. The transpose of this matrix equals itself, right? This reflects here, that reflects there, that reflects there. What's on the diagonal doesn't go anywhere, right? It's sort of a mirror image of itself along the diagonal of this matrix, going from the top left to the bottom right. So that's another example of a symmetric matrix. So the set of symmetric n by n matrices is a subspace of M sub nn, and you can show it's closed under addition and closed under scalar multiplication. Okay? And so using the same operations, it's closed under addition and closed under scalar multiplication. That makes it a subspace of M sub nn. Okay? If you add two symmetric matrices, you get another symmetric matrix. If you multiply a symmetric matrix by constant, you get another symmetric matrix. Again, using the same definition of addition and scalar multiplication that we used on M sub nn, right? And so if M sub nn had a weird version of addition, if we chose a different definition for addition in that vector space, my subspace would have to satisfy that weird definition of addition instead. Okay, so it has to be the same as the larger vector space, same operation, no matter how weird it may be. Okay. Okay. So the set of symmetric n by n matrices is a subspace of M sub n using the same theorem from before. Okay? Okay. Okay? And also the upper triangular matrices, the lower triangular matrices, the diagonal matrices, those are three more examples of subspaces of M sub nn. Okay? So the upper triangular matrices, the lower triangular matrices, the diagonal matrices. Those are three sets that are subspaces of M sub nn. okay? Okay, so for homework, what I want you to do is I want you to read examples 1 to 10 in 4.2. Okay, so we're going to read examples 1 to 10 in 4.2. Okay, so in the textbook in section 4.2, there's 10 examples. And so I want you to read all 10 of them. Okay, it'll help you understand what a vector space is. Okay, and so another theorem. This is going to be theorem 4.2.2. And so in this theorem, if W1, W2 to WR are subspaces of a vector space V, then the intersection of these subspaces is also a vector space. Well, is also a subspace of V. Okay, so theorem 4.2.2 says if you have R subspaces of a vector space V, then the intersection of all R of them is another subspace of V. Okay? And so you can show it's closed under addition and scalar multiplication again. So if you consider the intersection of these R sets, W1 intersected with W2, intersected ... intersected W sub R, if you take any two vectors in the intersection of those R sets, you're considering vectors that are in all R of them. And if you add them together, you're adding two vectors that are in all R of these sets. Well, separately, each of those vectors are in W1, and if you add them, the result is in W1. Also, those two vectors have to be in W2, and if you add them, they're both still in W2. And so on, up to including the last one. The two vectors are also in W sub R, and if you add them, they're in WR. And so that means when you add two vectors in the intersection of R subspaces, the result is in each of the R subspaces, and so it means it's in the intersection of the R subspaces. And so addition is closed under the intersection, in the intersection of those R subspaces. Okay, and very similarly, if you take a vector in each of these subspaces, or a vector in the intersection of these R subspaces, and you multiply it by a constant, that K, that constant multiple of your vector has to be in W1 and W2 all the way up to and including WR. And so it's also in the intersection. And so the intersection of these R subspaces, it's closed under addition and scalar multiplication again, and so it has to be a subspace of V also. So using the same process, you can show so I just proved for you is that this theorem holds, that the intersection of these R subspaces is also a subspace of V, because you have closure under addition and scalar multiplication. Okay? Okay. Okay, and so that is that. And so that's our discussion on vector spaces and subspaces of vector spaces. It's difficult when you first are introduced to it, okay? It can be very simple if you spend enough time studying it. And so what you need to do is you need to read examples 1 to 10 in section 4.2. You need to understand what a vector space is. You need to show how something is a subspace of a vector space by showing it's closed under addition and scalar multiplication, okay? Closure under addition is axiom 1. Closure under scalar multiplication is axiom 6, right? So there's 10 axioms. And so the theorem where we show something's a subspace of something else only requires axioms 1 and 6 out of all 10. And so it's a much faster way to show something as a vector space by showing it's a subspace of some given vector space, okay? But again, in order to show something's a subspace of a vector space, you have to also know that overarching set is itself a vector space. So at some point, you do have to use the 10 axioms to show something as a vector space. Mathematicians have to show something at some point was a vector space to eventually show that other things were subspaces of vector spaces, if that makes any sense. So the 10 axioms overall, in the end, are what's most important. And so all of this is built on 10 axioms. But once you learn about vector spaces, once you find that a lot of things are already vector spaces, you can start finding that more things are vector spaces in less time and with less effort by showing things are subspaces instead of vector spaces. Okay, so that was a lot. So vector space, subspaces, 10 examples. Okay, work on those 3 things. Okay, and I'll see you next time. Bye.